Hello, I am Akshat Kochak, and today we are discussing the end semester examination question paper of analysis and design of algorithm. So, first question is analysis the time complexity of the quick short algorithm in average case and provide step-by-step explanation. So, first of all, quick short is one of the most popular sorting algorithms which uses the divide and conquer problem solving approach. So device step is divide the problem into smaller subproblem and partitioning into two smaller subarrays around some pivot element. To do this, we use a partition method inside the quicksort function, which returns up index of the pivot after the partition. So it will be solved by two methods, problem 1 and problem 2. Uh, Now, average case time complexity analysis of quicksort. So, when we select the pivot randomly during the partition process, partitioning is highly unlikely to happen at the same way at every level. So, in the average case, the partition process will be generated by a combination of good and bad splits, where good and bad splits will be distributed randomly in the recursion tree. So here is the recursion tree method. So first of all, there is the first method n1, then step by step we solve it and we get the next solution for below it. Question number second, critically evaluate the star sense matrix multiplication and compare the time complexity with the traditional matrix multiplication method. So stars and metric multiplication is the divide and basically a divide and conqueror approach for the solution of metric problem. So the usual metric, the traditional matrix method multiply each row with the each column to achieve the productive product of the matrix. Though here for finding the time complexity taken by the approach, we use O to the power order of n to the power 3, since it takes two loops to multiply. Stars and metal were introduced to reduce the time complexity from O to the power O n to the power 3 to O n to the power log of 7. So here are some formulas to use to multiply the matrix. Now, time for the time complexity, we can solve the recurrence relation for Starson algorithm using substitution method. So let us assume that to tn equals to order of n to the power log 7. So that is the time required to multiply 2 and n to the nx n into n matrices using Starson algorithm is bounded by constant times n raised to power of log base 2 of 7. Then we can write tn equals to 7 of tn, and similarly we will proceed the method, and we will, after getting some value, we need to prove that tn is equals to o n to the power log 7 by the induction. So we will solve this question like this, and t to tn will be our tn less than equals to 7 by 2 cn to the power log 7 plus o n to the power 2, and we will put this value. Therefore the we have shown that the tn is equals to o n uh, to the power log 7, which means that the time required to multiply 2 nx n into n matrices using Starson algorithm is bounded by the constant time n raised to the power of log base 2 of 7. Question number third, evaluate Prim's algorithm for finding minimal spanning tree and provide a real world scenario where it can be applied. So Prim's algorithm is a greedy algorithm used for finding the minimum spanning tree of a weighted undirected graph. The algorithm starts with an arbitrary vertex and then repeatedly adds the minimum weight edge and that connects the current tree to a vertex not yet in the tree. The algorithm terminates when all the vertices have been included in the tree. The step of Prim's algorithm are as follows. First of all, we will start with an arbitrary vertex and add it to the MST, the minimum spanning tree. Now repeat the following until all vertices are in the minimum spanning tree. Among all the edges connected to a vertex in the minimum spanning tree to a vertex not yet in the minimum spanning tree, find the one with the minimum weight, and at last add the vertex at the other end of the edge to the minimum for the minimum spanning tree. Now, real world scenario will be that the Prim's algorithm can be applied on various fields such as network design, transportation, and logistics. For example, consider a scenario where a company needs to build a network for roads connected multiple factories and warehouse in a different location. The cost of building each road varies depending on the distance and terrain between the location. The company wants to minimize the local cost of the building the roads while ensuring all factories and the warehouse are connected. In this scenario, the location can be representation as vertices in the graph, and the cost of building each road can be represented as the weight of the edge connecting to the vertices. The application of the Prim's algorithm can help the company to find the minimum cost of building the roads while ensuring that all the locations are connected. The MST obtained from the algorithm would provide the optimal solution for the company's problem. The second part of question number third is analyze the Hamilton cycle and provide an example of how they can be used in a real life application. So Hamiltonian cycle in a graph is a path that visits each vertex exactly once and returns the starting vertex. A graph that contains a Hamiltonian cycle is called a Hamiltonian graph. Finding Hamilton cycle in a graph is a well-known NP-complete problem, which means that it is believed to be computationally different to solve for the large graph. Here is a small example of Hamiltonian graph. So real life application can be seen as one example for in the field of transportation and logistics. Consider a delivery company that needs to deliver package to the set of customer in a city. The company wants to minimize the total distance traveled by the vehicles while ensuring that each customer is visited exactly once. This problem is known as the traveling salesman problem, which is equivalent to finding a Hamiltonian exam cycle in a complete graph. By finding the Hamiltonian cycle that visits each customer exactly once and has a minimum total distance, the delivery company can optimize its delivery routes and minimize the travel time and fuel cost of its vehicles. In summary, Hamiltonian cycle have important application in the various fields including transportation, logistics, computer science, and network design. By finding the Hamiltonian cycle in a graph, we can optimize the delivery routes for the following company, the route data packets in a network, or solve the other optimization problem that involves visiting each vertex of a graph exactly once. Question number four is apply analytical perspective to develop a greedy algorithm for the sequencing unit time jobs with the deadlines and profit. Discuss the pros and limitation. So the problem of sequencing time unit time job with the deadlines and the profit is a classical scheduling problem, which is a set of job in a different processing time, deadlines, and profit needs to be scheduled on a single machine. The step of the greedy algorithm are as follows. Compute the profit to deadline ratio for each job, then sort the job in non-increasing order for their profit to deadline ratios. Schedule the job in the order starting from the earliest valuable time slot. Pros are greedy algorithm are simple and easy to implement. The greedy algorithm are sequencing unit time jobs with deadline and profit, has a time complexity of O n to log n for sorting the jobs, which is efficient. The algorithm can provide the optimal solution for the problem where the jobs have a common deadline. Limitation of the greedy algorithm are that it does not always provide an optimal solution. The algorithm does not consider the processing time of the job. The algorithm assumes that each job can be completed within a unit time, which may not be realistic in some real life scenarios. Now, question number five, derive the time complexity of iterative and recursive version of the Ebonic function to compare their efficiency in each case. So the recursive version of the Fibonacci function generates the nth Fibonacci number by recursively calling itself with the previous two numbers in the sequence. Where so it shows like Tn is equals to Tn minus 1 plus Tn minus 2 plus order of 1, where Tn is the time complexity of the function, uh, And the base case of the recursion is when n is 0 and 1 and the function returns 0 or 1 respectively. The recursion tree of the Fibonacci function has a binary structure, and each level of the tree has two recursive calls. Therefore, the total number of nodes in the tree is 2 to the power n, and the time complexity of the function can be expressed as t n is equals to or 2 to the power n. The iterative version of the Fibonacci function generates the nth Fibonacci number by iterating over the sequence and sorting the previous two numbers. So the iterative version of the Fibonacci function is more efficient than the recursive version of the large value of n because it has a lower time complexity. Question number 5. Explain the chain matrix multiplication with the suitable example. So the chain matrix multiplication is a problem which is a sequence of a matrices needed to be multiplicated to obtain a final matrix product. So the objective to find the optimal order of multiplication that minimize the total number of the scalar multiplication required. Let's consider an example to illustrate this problem. So for example, there are three matrix A of dimension 10 to 30, B of 30 to 5, and C of 30 to 5 to 6, 5 into 60. To obtain the final matrix product ABC, we can use two different orders of the multiplication. First, we can use ABC, second order ABC, and we can then use the traditional method also. Now, so we can use matrix Ij is equals to minimum M Ij Ik plus M K plus 1 J plus dim I into dimension K plus 1 into dimension J plus 1. So by computing the minimum number of scalar multiplication for each sub problem using dynamic problem, we can obtain the optimal order of multiplication. So in conclusion, chain matrix multiplication is a problem in which a sequence of matrices needs to be multi, multiplied to obtain a final matrix product. Question number 7. Use the critical lens to describe the traveling salesman problem using dynamic programming and discuss its potential benefit and limitation in solving optimization problem. So traveling salesman problem TSP is a classic optimization problem that involves finding the shortest possible route that visits every city in a given set exactly once when and the return to the starting city. So dynamic programming is a technique that is involved breaking down a problem into smaller subproblem and solving each subproblem only once, sorting the solution in a table for later use. In the case of TSP, dynamic programming can be used to be find the optimal route that visits every city exactly once by breaking down the problem into sub-problem of smaller size. So the potential benefit of using the dynamic programming to solve the TSP problem is that it can lead to the optimal solution of the in some cases. However, the limitation of this approach is that it is only efficient for the small problem instances. Furthermore, the use of dynamics programming to solve the TSP problem may limited by the assumption made by about the problem, such as the assumption that the distance between two cities is known in advance. The real world scenarios, the distances between the city may be subject to change, and the additional constraints such as the time windows or capacity constraint may need to be considered. Question number 8. Analyze and compare the class P, NP, NP hard, and NP complete problem. Discuss their significance in a computer science and their potential in real world applications. So class P, which is known as polynomial time, the problem in this class can be solved in a polynomial time, which means that the time is required to solve the proportional to a polynomial function of the input size. These problems are considered efficient and can be used to solve a reasonable amount of the time for the large inputs. Now NP, non-deterministic polynomial time. The problem in this class can be verified in the polynomial time, but there is no known algorithm that can be solve them in a polynomial time. These problems are considered as to be different and may require exponential time to solve. Example of NP problems include the traveling salesman problem and knapsack problem. NP hard, non-deterministic polynomial hard. These problem are the that are the at least as difficult as the hardest problem in the NP. This means that if an NP hard problem can be solved in a polynomial time, then all the problems in NP can be solved in a polynomial time as well. Example of NP hard problems include a Boolean satisfiability problem and the graph coloring problem. NP complete. These are problems that are both in NP and NP hard. This means that they are difficult to solve and may require exponential time, but they can be verified in a polynomial time. Example of NP complete problem including the traveling salesman problem and the knapsack problem. The significance of this class is lies in their practical implication of solving their problems. Every problem can be used solved efficiently, and many real world problems are generally considered to be difficult, but they often arise in a real world application such as scheduling, logistic optimization, etc. Thank you.